So in this session, we will see distributed parameter synthesis algorithms for time automata. So we saw two algorithms previously, the parametric reachability algorithm and a trace preservation synthesis algorithm. So these algorithms are costly. So we'll see how to improve their performance with distributed algorithms. So why are those algorithms very costly? First, you remember that all problems are undecidable, so they can actually last forever or use infinite memory. But in fact, even for finite parts, they use a lot of time and a lot of memory. Why? Because we have to use polyhedra operations, and those operations are very costly. In addition, we know no efficient data structures such as BDD or DBM as we use for time automata. We know no such data structure for parametric time automata. So there are a few attempts to propose parametrized DBMs, but it is definitely not as efficient as the DBM used, for instance, in UPAL. So an idea to try to increase the efficiency, to decrease the computation speed, is to use clusters. So I don't know if you are all familiar with what is a cluster. A cluster is a large set of nodes. A node is a computer. So it is a computer with its own memory, its own hard drive, and its own processors, one or more. And all those computers communicate with each other over a network. So a first naive approach could be as follows. To get a distribution of the EFSynth algorithm would be to have a bounded parameter domain. So we put bounds on all the parameters, and we cut our domain into small parts. And then we give each computer its own domain to compute. A drawback is that if some of the parameter subdomains require much more analysis time than others, then some nodes will have a large work, whereas others will be very fast and will be idle after a very short time. So what we did in the past 2 years is to go for master-worker approaches. So a master is one computer in the cluster that will be leading everything, whereas the worker just do what the master asks them to do. So the workers will run a hybrid algorithm. Hybrid why? Because it is a parametric reachability preservation. It will be inspired by this reachability synthesis algorithm and also the trace preservation synthesis, because we just explore a limited part of the state space and we take advantage of one integer reference valuation. So this is based on integer points. We will guarantee the coverage of all integer points, but we cannot guarantee with 100% certainty that all rational valued points will be covered. Also because, once more, this is undecidable, so we know that we will miss some parts. What will the master do? The master will just be responsible for distributing the work among workers and gathering the result. Let us go in a bit more details. So we have one master node communicating with workers. The worker will ask the master for a point and then will call an algorithm to generalize the behavior with a constraint. And the master will just be responsible for the smart repartition of data between the workers. So we did a lot of experiments with many different heuristics and algorithms, and it's not trivial at all. It depends on the case studies, it depends on many other things. In general, the most efficient distributed algorithm that we experienced is a domain decomposition scheme, actually dynamic domain decomposition. So the master will initially split the parameter domain into subparts and will send them to the workers. Then the worker will try their best to find valuations that are correct into the subdomain and then send the result to the master. And when a worker has completed its work, then the master will find the least efficient worker and cut his job into two parts and give one of them to the worker who finished his job. So graphically, this looks like this. This big part is a set of parameter evaluation. We don't know yet which ones are good, which ones are bad. This is what we want to achieve here. We focus on integer points, but I want to be clear that the algorithm still synthesizes most of the rational valued points. But just we have to focus on something, so we try to at least cover the integers, and usually we also cover a lot of rationals. So we split the domains and give a part to each of the workers, okay? And this has many advantages that makes the efficiency higher. Then, during the algorithm, we have a dynamic splitting, where when a worker has finished covering all its points, it will ask the master for more work. So the master is finding a worker that only covered a very small part of its domain. So it will cut it into two parts, give one of them to the second worker, and leave the unfinished to the ongoing worker. And the part that is already totally finished is just dropped because it is finished. And so the master will balance the workload between the workers that way. So we implemented this domain decomposition scheme in IMITATOR using the MPI paradigm, so the message passing interface. And we got results that were faster up to 44 times than only one computer computing EFSint using 128 nodes, so 128 computers in a cluster working together. So this gives the first version of distributed algorithms. So 44 times faster is actually very nice, but it's 44 times faster with 128 computers. So with 128 computers, we could actually wish to be 128 times faster. So we still have a large improvement, so we could be at least 3 times faster. And 44 times faster is the best experience. For some of them, it was much lower. So we still have a large space for improvement. And we are also interested in multi-core parameter synthesis. So most computers now have many cores, at least 4 and more, especially in clusters. So we could want to perform multi-core synthesis for the EFSint problem. So let us now see some tool support in the next sequence.